All right, so this is chapter 8, which has to do completely pretty much with like reactions. So we're going to first start off with, balancing reactions and why we have to balance them. Then we'll get into the reaction types and how to predict products of a reaction. And then finally, we will get into the energy of reactions. So, the chemical equation in general looks something like this. Your reactants are the starting substances for the reaction, which show up on the left-hand side. So in this case, it would be nitrogen and oxygen. And then your products are the ending substances of the reaction, which show up on the right side. So in this case, it would be your N2O2. Now that arrow represents the change between the reactants and products, and when we verbally talk about the reaction, we would to talk about the arrow, we would say yields. So for this, we could say nitrogen and oxygen yield dinitrogen dioxide. So coefficients are the large numbers in front of the substances, remembering that the subscripts are the small numbers right above. Right after the symbols. So coefficients are large numbers in front, and that tells us how many of the products and reactants are needed or used in the reaction. If we have an arrow with a triangle, like you see there, that represents that heat was supplied to the reaction. So that tells us that we needed heat in order for this reaction to occur. And then you also see those phases or states of matter shown in the parentheses. And so S stands for solid, L stands for pure liquid, G stands for gas, and AQ stands for aqueous. Remember that aqueous means that that substance is dissolved in water. So we talked about the law of conservation of energy, but there's also the law of conservation of mass. And the law of conservation of mass just states that matter cannot be created nor destroyed. It can only be rearranged. So what that essentially means is that we need the same amount of matter in the reactants as we do in the products. And so in order for that to happen, we have to balance these equations out. So in order to balance equations, we add in those coefficients. So you can see here there are 4 hydrogen atoms on the left. They've been rearranged on the right, but you still have those 4 hydrogen atoms on the right. You've got 2 oxygen atoms on the left and 2 oxygen atoms on the right. So if we didn't balance this equation and we just said H2 plus O2 gives us H2O, you would have 2 hydrogens on the right, 2 on the left, but you would have 2 oxygens on the left, and somehow you're now missing an oxygen on the right. So we had to balance this equation in order to get us the same amount of mass on each side. So when we balance chemical equations, the most important thing to do first is to check that the formulas are written correctly. So make sure that you're using the rules that I taught you in chapter 6. The biggest mistake that I normally see is students just put elements together and they don't think about the charges if it's ionic. So for example, zinc chloride, they sometimes just write ZnCl. And don't think that zinc has a positive 2 charge and chloride has a -1 charge, so we need 2 chlorides. So be sure to remember to check your writings of your ionic compounds especially, but also you do need to remember those diatomic elements as well. So the big 7, we start at 7, which is nitrogen. We move over and make a 7, so nitrogen, oxygen, fluorine, and then we go down to chlorine, bromine, iodine. Those are our 7. And then lastly would be hydrogen, H2. So if the formulas of your reactants or products are not correct before balancing, you won't get the right balancing equation as well. So you really have to make sure that you're doing all the work behind the scenes to make sure that your formulas are correct before we go ahead and balance them. Now, once our substance are written correctly, we will not ever change those to make more atoms. So let's say, for example, we have zinc chloride, ZnCl2, and for whatever reason you want another zinc, you cannot just change it to be Zn2Cl2. That doesn't work. You also can't change it to be Zn2Cl4. That doesn't work. We can only add coefficients to the front. So, for example here, if we needed some more of the, let's say we needed more oxygen for this example here with the iron oxide, we would need to put a 2 in front of the whole thing to say that we need some more oxygens. You can't just say, all right, I want to change it to Fe2O6. That doesn't work. Okay. It also doesn't work to say Fe4O6. You always have to deal with your lowest subscripts, and then our coefficients in front do the work. So how did I get 4 and 6? It's very similar to the parenthesis type of atom counting. Remember that if you've got like nitrate or carbonate in a parenthesis, that means we have more of those. The same thing happens to our coefficients. So 2 Fe2O3 tells me that I need to take 2 times 2 to get me 4 irons and 2 times 3 to give me 6 oxygens. So here are some tips for balancing chemical equations. At first, you're going to want to ignore the diatomics. You can't ignore them the whole time, but at first you're going to want to ignore them because those are going to be fairly simple to deal with at the very end. It gets a lot more complicated if you try to deal with them first. My second suggestion would be to look for polyatomics on both the product and reactant side that stay together and balance those. So what I mean by that is if you have SO4 on the reactant side and it stays together as SO4 on the product side, you want to balance those first. Then I would say balance your metals. So after the polyatomics, try to do the metals. Then any nonmetals except for H and O. Okay, leave those for the end. At this point, I would probably also balance any diatomic that is not H or O, and then the H and O comes last. And the reason for that is because a lot of times we're dealing with those, and they've got kind of an odd numbered split usually. So if there is an even odd split, for example, we've got barium chloride on the left and aluminum chloride on the right, we're going to balance with the least common multiple to make 6 on each side. So we would need 3 barium chlorides to make 6 chlorides on the left and 2 aluminum chlorides to make 6 aluminum chlorides on the right. And all coefficients must be in their lowest whole number possible. So what I mean by that is you can't have like 6, 2, 4, and 8. You would have to reduce that down by 2. So you would have 3, 1, 4, and 2, or whatever I had to say there. So those are just tips on balancing chemical equations. Use this order, and then here's kind of an even odd split kind of situation, and then coefficients. So here is my method for balancing chemical equations. I typically make a list right underneath that arrow, and that list includes all of the different elements or maybe polyatomics that I'm dealing with. You can see here that I have the polyatomic NO3 on both sides. It doesn't split up. So you can keep it just the same. You can keep it as just NO3 and count that as a group. If it were to split up, you would want to split it up into nitrogens and oxygens. But this one doesn't split up; it stays as NO3, and I don't see any other nitrogens or oxygens anywhere else. So make that list underneath the arrow, and then go ahead and count on each side. So I had 1 calcium on the left. I have 1 calcium on the right. I have 2 chlorides on the left and 1 on the right. I have 1 silver on each side, and I've got 1 nitrate and 2 nitrates. So for your viewing pleasure, I have put the unbalanced elements or groups in in yellow for you. So at this point in time, we've got chloride and nitrate unbalanced. Now, the first thing that I'm going to do is I am going to put a 2 in front of silver nitrate to try to balance out that nitrate group. So when I did that, I now have 2 nitrates on each side. That makes it balanced, so I turned it to a gray color for you. But when I did that, that also changed my silver to now have 2. By putting that 2 there, I got 2 nitrates, but I also got 2 silvers from that. And so I now have 2 silvers compared to the other side just has 1. So my silver is now unbalanced. My chloride remains unbalanced. So to try to balance those out, I'm going to put 2 in front of silver chloride. And so what that does for me is it changes my chloride to 2. It changes my silver to 2. And so if we take a look all the way down this list, I have 1, 2, 2, 2. And on my product side, I have 1, 2, 2, 2 as well. So that's my advice for balancing these equations is make a list underneath and then change coefficients, and as you change them, also change the other items underneath that change. So here's my overall count there: 1 2 2 2 and 1 2 2 2. That's what we need to get to. So here's another example, and you can practice it if you want. Otherwise, you can watch along and watch me balance it. Okay, so my first thing to do here is going to be to count out my different elements. So phosphorus over on the left, I have 4. On the right side, I have 1. Oxygen, I have 10 here, 1 here, so I have 11. On this side, I have 4. And then my hydrogens, I have 2 on the right and 3 on the left. So the one I'm going to start with first here would be phosphorus, trying to get our phosphorus balanced, and then we'll deal with the rest. So to get my phosphorus balanced, what I'm going to do is I'm going to put a 4 over here. When I put a 4 over here, it's going to change everything on the right side. So I got 4 phosphorus. I now have 4 times 4 gives me 16 oxygens. And then I get 4 times 3 gives me 12 hydrogens. Now in this case, I can see the thing that I'm looking at right here is that oxygen in my water is an odd number. We're going to have to get that to an even number. So I'm going to choose to do hydrogen next. And so I need to get hydrogen from 2 up to 12. So I'm going to try and put a 6 here. When I put a 6 here, what that's going to do is it's going to change my hydrogen to 12. And it's going to change my oxygen here. I've got 10 from the P4O10. So I've got 10 from that. And now I've got 6 times 1 gives me 6. So 10 plus 6 gives me 16. If I take a look, I'm good here with phosphorus 4 and 4, 16 and 16 and 12 and 12. So here is my balanced equation. I have my 1, but we don't write the 1. I've got 6 waters and I've got 4 phosphoric acids there. All right, on our next one, On our next one here, we've got aluminum sulfate reacting with calcium hydroxide to form aluminum hydroxide and calcium sulfate. So for this one, let's count it out. I have 2 aluminums, I've got 3 sulfates, I've got 1 calcium, and I've got 2 hydroxides. On the product side, 1 aluminum, 3 hydroxides, 1 calcium, and 1 sulfate. So my first thing to do here would be to try to balance out those polyatomics. I'm going to first start out with my sulfate, a 3 to 1. And so what I'm going to do here is I'm going to put a 3 in front of calcium sulfate to try to get 3 of those. So I now have 3 sulfates, but I now have 3 calciums as well. The next thing to do would be to try to do my hydroxides. Those are kind of messy, so let's deal with our metals next. Since I changed my calcium to 3 on the product side, let's try to balance that out with 3 over here. So now I have 3 calciums and I have 6 hydroxides. And then hopefully what you're seeing here now is that I have 2 aluminums to go. So a 2 there gives me 2 aluminums, but it also now gives me 6 hydroxides. So I'm good here. 2 aluminums on each side, 3 sulfates on each side, 3 calciums on each side, and 6 hydroxides on each side. So sometimes you got to go, or you don't have to, but sometimes it helps to go a little bit out of order of my list and maybe skip down to metals, and then your polyatomics sometimes fall in place. My suggestion would just be to pick something, start with it, and then see where it changes and goes from there. So I want you guys to practice this one here. We've got hydrochloric acid and aluminum forming aluminum chloride and hydrogen. We've got calcium phosphate plus silicon dioxide forming tetraphosphorus decaoxide and calcium silicate. Now, please notice on that one there that the phosphate does not stay together. So PO4 does not stay together as PO4 on the other side. So you do have to separate that out into phosphorus and oxygen separately. And then lastly, we've got hydrogen sulfate and hydrogen iodide, forming hydrogen sulfide and iodine and water. All right, so if we take a look here, here's how we're going to go about balancing this. We are going to have hydrogen, chloride, and aluminum. So I've got one hydrogen, one chloride, and one aluminum. I've got two hydrogens, three chlorides, and one aluminum. So if I take a look, my metals are already balanced. I'm not going to start with aluminum. I'm not going to start with hydrogen. I will start with my chlorides first. So to get three chlorides here, I'm going to do a 3 here, which is going to change my hydrogen to 3 and my chlorides to 3. So at this point, now I've got aluminum and chloride balanced. What's not balanced is my hydrogen. So what happens in balancing sometimes is that you're going to have to change what you already thought you were going to have to do. And so what we might have to do is we might have to take a look. Okay, I've got 3 hydrogens and 2. 3 to 2, that's an odd even. So we're going to come to that common number of 6. And so to get 6, I need a 3 on my product side, and I need to change that 3 over here now to a 6. So now I've got 6 hydrogens on my product. I now have 6 chlorides. On my product side, I now have 6 hydrogens. But let's take a look. What's not balanced? My chlorides are out of balance now, and that's okay. So to get me from 3 to 6 on my product side, I need a 2 there. By putting a 2 there, yeah, I get my 6 chlorides, but now I also unbalance my aluminums, and that's fine. What I need to notice now is that I need a 2 here in front of aluminum, and then we're all good. So if you take a look, I've got 6 hydrogens, 6 chlorides, and 2 aluminums. Here's what it would actually look like. Okay, 6, 2, 2, 3, and I'll go ahead and count them for you again. So hydrogen, I have 6, chloride, I have 6, I have 2 aluminums, and then on my right-hand side, I have 2 aluminums, I have 6 chlorides, and I've got 6 hydrogens. All right, on this one here, I am dealing with calcium, I have phosphorus, I have oxygen, and I have silicon. Okay, if we take a look here, my calcium, I have 3, I have 2 phosphorus. My oxygen's tricky. I got to remember I have 8 here, and then I've got 2 more there. So I've got 10 oxygens there, and I've got 1 silicon. On my right-hand side, I've got 4 phosphorus. I've got 10 oxygens here, and then another 3 here. So I have 13 oxygens. I have 1 calcium. I've got 1 silicon over there. So the first thing I notice is my calcium. So let's try to balance out my calcium. By doing that, I'm going to put a 3 here. When I do the 3 there, let's take a look. We get 3 calciums. I now get 3 silicon. And then we got to count our oxygens again. I get 10 from this P4O10 plus another 3 times 3 is 9. So I get a 19 there. So my calciums are balanced now. That's pretty much it. So let's try to do maybe some phosphorus. So my phosphorus, if I do that and put a 2 here, I know by putting a 2 here, that might screw what we just did up, but that's okay. So putting a 2 there, I now have 6 calciums. I've got now 4 phosphorus, and the reason for that is I've got 2 times 1 gives me 2. 2 times 2 gives me 4. Now I have, again, 2 times this 8 gives me 16, plus another 2 gives me 18 oxygens, and my silicon didn't change there. Okay, let's take a look here. I just want to erase some of this, make it a little bit easier to see here. All right, so then now I'm dealing with, I can see that my calciums are unbalanced again. So let's go back and try to fix that. So to fix that, let's change this 3 into a 6. So I now have 6 calciums. I have 6 silicons. And now I have 6 times 3 is 18. 18 plus 10 gives me, I now have 28 oxygens. All right, so now what's good? I'll put a check by it for now. We've got calcium balanced, we've got phosphorus balanced, we've got to deal with oxygen and silicon. So to deal with oxygen and silicon, let's deal with my silicon. So I'm going to try putting a 6 here. 6 changes my silicon into 6. But then we got to take a look at oxygens. I get 2. 2 times 4 gives me 8. Times 2 gives me that 16. 6 times 2 gives me 12. 12 plus 16 gives me 28. 28 and 28 are good. 6 and 6 are good. 4 and 4. 6 and 6. So here's our final balanced equation. I'll clear the screen here so that you can see the true answer. 2, 6, and 6. This was a pretty difficult one because that phosphate group didn't stay together. Just remember that when you're balancing these things, it's okay to change numbers that you thought were going to work. That's totally fine. That's part of the balancing process. The big thing at the end of the day is to be sure that you're getting your answer. So calcium, I have 6 and 6. Phosphorus, I have 4 and 4. Oxygen, I had 28 and 28. And then my silicon, I have 6 and 6 as well. All right, now this last one, I've got a lot of hydrogens all over the place. I've got sulfur, I've got oxygen, and I've got iodine. So hydrogens on the left-hand side, I have 2 and 1 for 3. Sulfur, I have 1. Oxygen, I have 4. And iodine, I have 1. On the right-hand side, I've got 2 plus 2. I have 4 hydrogens. Sulfur, I have 1. Oxygen, I have 1. And iodine, I have 2. So for this one, since my sulfur is good, let's now move on to trying to get that the oxygens balanced. I'm going to leave that iodine kind of there for now because it's a diatomic. That becomes a little bit easier to deal with. So what I'm going to do here is I'm going to try to do my oxygens. So in order to get my oxygens balanced, I'm going to need a 4 here for my water. That is going to change my hydrogens as well. But for now, I have 4 oxygens. And then for hydrogens, I've got 4 times 2 gives me 8. And then another 2 gives me a total of 10 hydrogens on the right-hand side. So then if I want to take a look, okay, sulfurs are good, oxygens are good. I need to deal with my iodine and my hydrogen. So if I take a look here, I'm going to try to leave this one alone. So try to leave alone, because as soon as you start to touch that one, you're going to start to have to balance your sulfurs and your oxygens. Okay, so I'm going to leave that compound alone. I'm not going to try to add any coefficients here. What I'm going to try to do is I'm going to try to deal with my hydrogen iodide here. So let's try to get my hydrogen and iodide to balance to 10. So I'm trying to get to 10 hydrogens. I have 2 here. So I take 10 minus 2 gives me 8. I need 8 more hydrogens. So by putting an 8 here, that is now going to change my hydrogen total up to 10. Again, that 10 comes from 8 here, and then 2 from my hydrogen sulfate. And then from here, I now notice, okay, I now changed my iodine into 8 as well. This is nice and easy now. Hydrogens are balanced 10 and 10, sulfur 1 and 1, oxygen 4 and 4. So for this one here, I need to balance out my iodines. I have everything needs to be multiplied by 2 for this, so I need a 4 here to get me up to 8. If we take a look, we're now good with 8 and 8. I will again clear the screen here and give us the final totals just to check again. So we had 8, 4, and 4. Let's go through and count them again. Hydrogen, sulfur, oxygen, and iodine. My hydrogen, I get 2 here. I get 8 there. So 10. Sulfur, I have 1. Oxygen, I have 4. Iodine, I have 8. Over on the product side, I have 2 hydrogens here. I have 4 times 2 gives me 8 hydrogens there. Gives me that 10. 1 sulfur. I have 4 oxygens over here. And then my iodine, I have 4 times 2 gives me that 8. All right, so that's how to balance chemical equations. If you are struggling with balancing them, here are some tips. So if you're struggling to get a balanced equation and you have a diatomic element, balance all the elements first. That diatomic can come at the end. It's typically the easiest to balance just because if you can get your one side to be even, you can always get that diatomic to get to the number that you need. Once you have all the other elements balanced, count how many of the diatomic element you have on the other side, and then multiply all the other coefficients found to that point by 2, and then put that number from the previous step in front of the diatomic. This method here that I'm talking about typically works well for combustion reactions, and combustion reactions typically deal with a carbon-hydrogen compound plus oxygen to give us water and carbon dioxide. So what I did here was I first balanced out my carbons and hydrogens. So I saw here C2, so I put a 2 in front of carbon dioxide. And then I saw H6, so I put a 3 here in front of water to give me that 6. So what that did now is it left me with 3 times 2, 3 oxygens, and then 2 times 2 gave me 4 oxygens. I was left with 7 oxygens on the right-hand side. What I'm going to do now is I'm going to multiply all the coefficients by 2 and add a 7 in front of that oxygen. So I had a coefficient of 1 here. 1 times 2 gave me that 2. 3 times 2 gave me that 6. 2 times 2 gave me that 4. And then I'm going to add that 7 here. The reason that I did this was because technically I needed like 7 halves oxygen on the reactant side, but you can't have 7 halves. So what I needed to do is multiply everything by 2, and then I can add that in. So if we go ahead and count this final balanced chemical equation, I have 4 carbons on each side. I have, for my hydrogens, I've got 12. And then for my oxygen, I have 14 on the left. And then on the right, I have 6. And 4 times 2 gives me 8. 6 plus 8 gives me 14. So we're all good there. That is typically a difficult problem. If you've got a diatomic, try to balance everything else first. And then if you just can't seem to get it to balance out, multiply everything by 2 and then put that that number of atoms that you had on the diatomic. Now, in this next one is just some more tips. Always keep track of how many elements you have and how they change when you add coefficients. Remember that when you add a coefficient, it changes the number of atoms that of everything that you have there. Never be afraid to keep trying to push further in balancing if it seems like you're stuck, but also at the same time, don't be afraid to start over if you feel like you've gone too far. Try to go as far as you can, but if there's a point where you feel like it's not going to go any further, then just erase everything you have and try over again. Lastly, feel free to reach out to me if you have any questions on any problems. Sometimes you just need a second set of eyes to help you with that. All right, this next little chapter are the signs of a chemical reaction. So there's a few signs that a chemical reaction takes place. One would be change in energy. So we could have thermal energy changing, which would give us a change in temperature. You could also have light or sound energy given off. Some reactions, produce quite a bit of light. Some produce a popping sound. Those are signs that a reaction are taking place. A precipitate forms. That's this kind of yellowish, brownish kind of color. A precipitate just means a solid forming in liquid. Gas being formed. You could have a color change, or you could have a production of odor. So what are the driving forces of a reaction occurring? There are kind of 4 different types of reactions that we can kind of think of. You could have the formation of a solid. Again, that would be like this picture in the top right with the yellow. You are adding a liquid into a liquid, and when those react, you get a solid product being formed. You have formation of gas, which would to us look like bubbling. Formation of water, it's not visible, but it is still happening. And so for this, you would have an exchange of ions and water being produced. Typically, that's going to be an acid-base reaction. And then you could have the transfer of electrons. This is one of the biggest types of reactions. We don't get into how that all works in this class. We can't see the transfer of electrons, but you would most likely see a change in the substances to tell us that the reaction is happening. So there are 5 types of reactions that we're going to classify in this class: synthesis, combustion, decomposition, single displacement, and double displacement. So a synthesis reaction could be simplified as saying taking A plus B and we get reaction or product AB together. And so in a synthesis reaction, 2 reactants combine to form one product. You can see here we've got sodium and chlorine gas, and those come together to form the nice tasty salt that we put on our food. You could also react sodium plus oxygen to get a sulfur plus oxygen to get a sulfur dioxide gas. You could take sulfur trioxide gas plus water to get us a sulfuric acid product. So again, you're taking 2 reactants and combining them to form one product. Synthesis, when you hear synthesis, try to think putting together. Combustion reaction happens when you have a substance reacting with oxygen to form oxides. And the most common combustion reaction are hydrocarbons. Hydrocarbons are just carbon-hydrogen molecules, and they're going to react with oxygen to form carbon dioxide and water. So there you've got methane plus oxygen to give us carbon dioxide and water. And then that second one is octane, which is gasoline, reacting with oxygen to form carbon dioxide and water. A decomposition reaction, you're typically going to have one reactant, and then that is going to break down into 2 or more new substances. So here we could say AB is breaking down into A plus B. If we take a look, we've got lead oxide being broken down into, or sorry, I should have technically said lead 4 oxide being broken down into lead 2 oxide plus oxygen. Here we've got calcium carbonate being broken down into calcium oxide and carbon dioxide. And lastly, we can technically take a hydrogen peroxide, and it doesn't naturally, you don't technically need heat for this to occur, but hydrogen peroxide, even in the brown bottles that you buy at the store, those will naturally break down over time into water and oxygen. The next one is a single displacement reaction, okay? And so for this one, I use the analogy of going to prom. So let's say a single person goes to prom, and then in the middle of the dancing time, that person kicks out one person's date, and so now they're dancing, and that other person is left on their own. So A comes in and kicks B out, so that now we've got B all by itself and AC together. So one element, again, is going to react with a compound to replace one of the elements, which results in that single element reactant being part of the product. That's a long, drawn-out way of just saying that we have a single element kicking out the element in the compound so that it's now alone, and then that single one is now part of the product. So here we've got zinc plus hydrochloric acid, and this one's kind of odd. You've got to take a look. We've got zinc kicking out hydrogen. Now, hydrogen doesn't come off as just H. It's got to come off as H2 because it's a diatomic element. So we get hydrogen gas coming off, and then we've got that zinc chloride. Here we've got copper coming in and kicking out silver. So now we get silver all on its own, and then we've got that copper nitrate as the compound. And lastly, we've got chlorine gas coming in and kicking out bromine. And that bromine's going to now be in its elemental form, and we're going to get salt, sodium chloride, out of it. Now, with a single displacement reaction, they don't always happen. In order for one of these reactions to happen, the single element on the reactant side, the one that's trying to do the kicking, needs to be more active. And what that means is it needs to be higher up on this list, okay? And so for a reaction to happen, something would have to be higher. So lead could be the single element. So that could happen. But if we tried this, silver plus lead nitrate, That will not happen because silver is lower than lead, so silver cannot kick lead out. Think of it kind of as a popularity game, again with the dance analogy. So lead is more popular than silver, so nitrate would be happy getting with it. So that lead is going to kick out that silver, and so in our products, we're going to get lead nitrate plus silver. So we went from there to there as our reactants and products. But again, silver isn't quite as active as lead, so it cannot kick it out. So that one would not happen. Now, most metals can replace hydrogen from compounds, whether those are acids or water. Most of these can replace the hydrogen. And so if we take a look, hydrogen is right here. Anything above hydrogen can replace it. So if we had, for example, iron trying to replace the hydrogen in the hydrochloric acid, that could happen. We have iron kicking it out. So we've got iron chloride plus our hydrogen gas. Okay, I didn't balance those, but that's essentially what's happening. However, when we go down below hydrogen, those cannot kick them out. So we've got copper, silver, mercury, and gold. Those do not react with hydrogen in acids or water. So if I try to do copper plus hydrochloric acid, nothing is going to happen. Copper cannot kick out hydrogen. That does not happen. So that one would form a non-reaction there. All right, the next one is double the displacement reaction. And so again, I'm going to start this one with a prom dance analogy. So what's happening here is you've got two couples that go to the dance. In the middle of the dance, they decide, okay, let's switch partners. And so the guys switch, and so now they're dancing with the new partners. So this one is kind of tough to see with these letters, but essentially what's happening here is that A and C switch. And so now A is going to be with D and C is going to be with B. And so we get AD plus CB. And so when I do these, I typically think of the first elements exchanging or the first parts of the compound exchanging, but some people think about the second parts. It's up to you. I just personally think about those first ones flipping. So some different reactions that happen here. We could have water and heat being formed. So if we react, typically it's going to be like an acid or base, or we could have some hydroxides. So if we react hydrochloric acid and sodium hydroxide, so hydrochloric acid is an acid, sodium hydroxide is a base. When we react those, we're going to get a salt and water and heat. So you're going to get some H2O water liquid, and you're going to get some heat. That next one, we've got calcium oxide reacting with hydrochloric acid. So we're going to get calcium chloride and water and heat there produced. If we could also have a solid being formed. And so I'll kind of go through this on the next page. But we have a whole giant table that tells us whether things are aqueous or whether they are insoluble. When I say insoluble, I just mean that it's a solid being formed. So you could have barium chloride and sodium carbonate forming barium carbonate and sodium chloride. You could have lead nitrate and potassium iodide forming lead iodide and potassium nitrate. Both of these, you can see here that we get solids in the product. So you can see there that the parentheses have solids, which tell us that the reaction took place. You could also have a gas being formed. So if I react sulfuric acid with sodium chloride, I get sodium sulfate and hydrogen chloride gas. So that could happen. I could also react hydrochloric acid with zinc sulfide, and we're going to get zinc chloride out of it and hydrogen sulfide gas. We could also have the indirect formation of gas from unstable products. So let's say I react hydrochloric acid with sodium carbonate. Initially, my products are going to be sodium chloride and carbonic acid, but carbonic acid quickly changes into some new products. So my carbonic acid is going to change into water and carbon dioxide. So you're going to get some new products made out of that. That's the one that I'd like you to know is that carbonic acid, H2CO3, is going to break down into water and carbon dioxide. So here's the big table. It's called a solubility table, and it tells us whether things are soluble or not. So if we take a look, we're going to use this. We're kind of going to use it like a multiplication table. You're going to find the two things that you want to deal with, and then you're going to take a look at what's in that box. So if I take a look and I see, all right, I want to be dealing with, let's say, zinc chloride. Zinc chloride, I'm going to find my zinc, I'm going to find my chloride, and I'm going to go down till I find what's in that box. If it says AQ, that means it's aqueous. It's going to be able to be dissolved in water. Let's do another example. Let's say I want to deal with calcium carbonate, CaCO3. I'm going to find my calcium. I'm going to find my carbonate. When I come here, I have an insoluble product, which means that it is a solid in water. Okay, insoluble just means that it is a solid in water. So if you want to make that note to yourself down here, insoluble just means a solid. We don't deal too much with slightly soluble or decomposition. Those are not super common substances that we're dealing with there. Let's see. I want to kind of generally teach you some of these rules. You don't need to memorize these. You will be given this table, but just so that it goes a little bit quicker, the rules for the memorizing kind of the solubility table, again, you don't need to memorize it. All right, so again, you don't need to have this chart memorized, but this typically helps you, like, so that you don't always have to look at that chart. So things are soluble or aqueous if they're a first column metal, if they're ammonium, or if they're nitrate. If they have the first column metal, NH4 or NO3, they are soluble or aqueous. Your chloride, bromide, and iodide are typically always going to be soluble as well, with the exception of silver, mercury, and lead. So for the most part, first column metals, ammonium and nitrate, those are always soluble or aqueous. And then our chloride, bromide, iodide are pretty much always aqueous as well, with the exception of if they're paired with silver, mercury, or lead. Now, your insoluble or your solids are typically going to be carbonates or phosphates, except for the first column, and then hydroxides, except for the first column. So typically, your insoluble solids are going to be carbonates, phosphates, and hydroxides, except when they are bonded with the first column. And again, you don't need to memorize this. It just helps get things going a little faster once you start to learn those rules. So I want you to first practice figuring out these reaction types. Again, the 5 options we have are synthesis, decomposition, combustion, single displacement, or double displacement. So take a pause, figure out the answers, and then come back for the answers. All right, so if we take a look at this first one, we've got iron chloride. And so iron chloride reacting with sodium hydroxide is going to give us iron hydroxide and sodium chloride. If you take a look here, we get a new solid formed. When we get that new solid formed, you should really be thinking about a double displacement. And if we take a look, that iron came in and swapped places with the sodium. So we now have iron hydroxide and sodium chloride. So that's what happened there. So that would be a double displacement reaction. In our next one, we've got a carbon and a hydrogen compound reacting with oxygen to form carbon dioxide and water. So that there should tell us that it is a combustion reaction. So a combustion reaction, again, typically involves a carbon hydrogen reacting with oxygen to form carbon dioxide and water. And this is propane gas there. Our next one here is hydrogen plus oxygen making water. We've got 2 things coming together to make one. That would be a synthesis. The next one would be carbonic acid decomposing into water and carbon dioxide. So that is a decomposition. And the last one is magnesium plus sulfuric acid, giving us hydrogen gas and magnesium sulfate. This one here, magnesium came in, kicked hydrogen out. So we get hydrogen all by itself, magnesium and sulfate. So this is a single displacement reaction. All right, now on this next slide, we are going to try to predict the products. You're going to balance them if we can get products, and then make sure to include phases. If you go ahead and figure out the products and you realize that it can't actually happen, then you can write no reaction. The reason that things may not happen would be the activity series. So if you're trying to do a single displacement reaction, which is one element coming to bump another element out of the compound. So if the single element is not higher than the one in the compound, then it will not happen. And then if you don't form typically a solid, a gas, or water, then a double displacement reaction will not form. So my advice for you on this one would be to go ahead, figure out what the products would be, and then think about, is that actually possible? All right, so if we take a look, we've got copper and iron nitrate. So initially, if we take a look, we might see that we've got these swapping places. So I'm going to go ahead and figure out what our products would be, and then I'll tell you if the reaction would happen. So copper is going to come on in and try to displace our iron. Copper exists as a +2 charge. So we're going to need nitrates, and each one has a minus charge. So we're going to need 2 nitrates. So it's going to be CuNO3 parentheses 2. And then we're going to get iron all on its own. So this would be aqueous. This would be a solid. But if we think about this, in our list, copper, which is the singleton, is going to try to displace iron. Copper is below iron on that list, and so this would actually form a no reaction for number 1. Okay, that no reaction again is because copper is not more active than iron. The single one has to be more active to kick it out. Now our next one, our products. We're going to switch these 2 first ones out. So I'm going to get sodium nitrate, Na plus NO3 minus. So I just need 1 of each. And again, what I would just suggest doing here would be to just kind of erase these charges once you figure it out. Okay, so use the charges to figure out what you want to do, but then consider erasing them. So sodium nitrate, if I take a look at that big chart, is aqueous. Again, that's aqueous because we've got the first column element and we've got nitrate. And then we also have magnesium is going to be paired with chloride. Magnesium has a +2 charge, chloride has a -1 charge, so we're going to need 2 chlorides. And again, before you say I'm all good and done, just kind of erase those charges there. Those don't belong in a formula. So if I take a look there, magnesium chloride is going to be aqueous as well. Since we have 2 aqueous solutions, this is also going to be a no reaction. You need to have a solid formed, or you need to have some sort of gas compound formed or water formed. And in this case, we get 2 aqueous solutions. So the first 2 are no reactions. This next one, magnesium is going to come in and try to kick out silver. And so we would get magnesium nitrate. Now, magnesium's got a +2 charge. Nitrate's got a -1 charge. So we're going to need 2 nitrates for that magnesium. And so erasing those charges. And then we are going to be left over with silver. So magnesium nitrate is aqueous. Silver would be our solid. And if we take a look at the list, magnesium is pretty high, and we're trying to replace silver. Magnesium being higher than silver, this is a go. This is a good equation here. So now we just got to go ahead and balance these out. I see that I have 2 nitrates on the product side. That means I need a 2 here. Once I have a 2 there, I'm going to need a 2 in front of that silver. Okay, so this here would be my full balanced equation. I have 1 magnesium, 2 silver nitrates, 1 magnesium nitrate, and 2 silvers. And then the last one here, I've got cobalt chloride with sodium phosphate. I'm going to switch these out. So I'm going to have sodium chloride. Sodium chloride is aqueous. And then I'm going to get cobalt, which has a +2 charge, and phosphate, which has a -3 charge. So I'm going to need 3 cobalts 2 phosphates. Again, I'm going to go ahead and erase those charges. Sorry. All right, so if we take a look here, we've got cobalt phosphate. And cobalt phosphate, if we take a look, is a solid, which is good. This reaction can happen. So now that we figure out that it can happen, let's go ahead and balance out our compounds. So right away I see I have 3 cobalts on my right-hand side. Let's put a 3 over here. When I do that, now I have 6 chlorides on the left-hand side. I now need 2 phosphates, so we're going to put a 2 there to get my phosphates to balance. I now have 6 sodiums, so I have 6 sodiums and 6 chlorides on the reactant side. I have 1 of each. That's nice and easy. I can put a 6 there and call that good. So first 2 were no reactions, second 2 do form reactions, and those are the balanced equations there as well. All right, so we need to talk about heat being used or produced in chemical reactions. So almost every reaction is going to involve some sort of thermal energy change. Sometimes it's so small that it's really not very measurable, but there is typically going to have to be a heat change. And the quantity of heat that is absorbed or released is known as the heat of reaction. And typically we're going to measure that in kilojoules. Kilojoules, Kj, is a measure of energy. And it's just 1,000 joules. It's just an easier number to look at. So reactions that release energy are called exothermic. The way that I remember this is that energy exiting, exo. Okay? And then reactions that absorb energy are called endothermic. So here I think energy entering, think endo. Sorry about that. Enter endo and exit exo. That's how I always remember these. Now, how can you see energy is exiting? Energy is exiting when it is a product, and it's entering when it is a reactant. So you can see here the difference between those two, where they are. Every once in a while, you'll see off to the side, sometimes they don't write it quite like this. Sometimes they'll say delta H equals negative 185 kilojoules. That negative 185 means that it was released. And here you would see delta H would say a positive 181 kilojoules, and that means that it is entering our equation there. So we can graph these on what's called a reaction energy diagram. And so in a reaction energy diagram, it can tell us quite a bit. Endothermic reactions are going to have a higher energy for the products than reactants, and that's because energy entered the system or was absorbed. And then exothermic reaction, our reactants had more energy than our products. So if we take a look at what these are actually telling us, is that here are our reactants. Okay, so our reactants are the first half of our energy diagram, and then our products are the second half. Now, the energy absorbed or the energy released is just the difference between the start and the end. So for this one, energy absorbed, we could say that this was that 150 kilojoules that was absorbed as a reactant. Okay, so we could say here, okay, maybe this was 50 kilojoules, and then up here we could say that was 200 kilojoules. In our exothermic reaction, we got to have our energy as a product. And so here we could say that this is maybe 200 kilojoules and this is 50 kilojoules. And so we could say that 150 kilojoules was released. So that's how we go about reading how much energy was gained or lost. We typically are going to put our reactant actually here. So A plus B, maybe giving us a B here. So we're typically going to put that by the line. And then the last thing I want to talk about is the activation energy. Activation energy is the energy required to get a reaction going. So the definition of activation energy is the energy needed to get a reaction going. And so to calculate our activation energy, you're always going to calculate that from our reactants to the peak. Okay. It has nothing to do with what's on the product side. It's always from reactant to peak. Nothing has to do with our products. The only time you're dealing with our products is when we look at endothermic versus exothermic and how much energy might be gained or released. So the last thing here would be one more practice problem. And so for this one, I want you to identify the reactants, the products, the change in energy, whether it's exo or endothermic, and calculate the activation energy. All right, so for this one, our reactants would be nitrogen monoxide, and our products would be nitrogen and oxygen. So that's our reactant, that's our product. The change in energy, when I'm asking for that, I'm going to take my products minus my reactants. So for this one, I'm going to take 100 kilojoules minus 50 kilojoules, and I can see that we needed 50 kilojoules as a reactant. Since it was 50 kilojoules as a reactant, that is going to make this endo. And the last thing I have to do is calculate my activation energy. My activation energy, I'm going to take my peak minus my reactant, so 250 kilojoules minus 50 kilojoules, that's going to equal 200 kilojoules. And that's my activation energy.